The purpose of this lab was to use a number of different methods to examine how geometric features influence the stress and strain within a planar specimen. The specimen that we used was a polycarbonate plate which had a width of 10 inches, a length of 12 inches, a thickness of 0.211 inches, and there was a hole at the center of the plate that had a radius of 0.5. The following equations relate normal vertical and horizontal stress to strain with the use of Poisson's ratio and Young modulus as constants of proportionality.
The first equation on this slide relates the net section stress with the magnitude of the load. The next two equations are the most applicable in this lab because they relate the horizontal and vertical stress with the distance from the center of the hole. Based on the last equation from the previous slide, we used MATLAB to plot the graph of the vertical stress versus the distance from the center of the hole. When the distance is less than 0.5 inches, which is the radius of the hole, there's a significant decrease in the stress. When you move further away from the hole, the stress decreases slower and approaches to zero.
With the use of SOLIDWORKS, we were able to analyze the stress concentrations in the model with a process called finite element analysis. In order to ensure the simulation was conducted under similar conditions to that of our experimental setup, when we created the model, we applied a symmetric constraint to the two cut edges and a roller constraint to the back of the plate in order to constrain out-of-plane motion of the plate. We then applied a 2,000-pound force to our polycarbonate plate and created a mesh, which enabled us to analyze the stress concentrations within the plate. Our study enabled us to reach the conclusion that stress around the circumference of the hole was much greater, which is shown by the fine nature of the mesh, whereas as you move further away from the hole, the stress concentrations decrease, which is shown by the coarse. With the use of our finite element analysis, we were able to obtain a plot of the vertical stress distribution across the plate. Our study showed that around the circumference of the hole, the stress distribution was non-uniform, whereas as you moved away from the center of the hole, the stress distribution became much more uniform. This is in keeping with Venant's principle, which states that when a point load is applied in the plane of a plate, the stress around the load point will be non-uniform, but by the time you move a width's length away from the point load, we can safely assume that the stress across the section is uniform. Our finite element analysis also enabled us to obtain a value for yield strength, which was 69.7. We then obtained a similar plot for shear stress distribution across the polycarbonate plate, which gave us similar results.
So here's the picture of the setup of the lab. You can see the hole in the very center of the plate. You can also see the stress and strain sensors, which are oriented horizontally and vertically. Here I'm going to talk a little bit about photoelasticity. So basically, when a load is applied on a piece of isotropic material, which is polycarbonate in our case, the material would lose isotropy in one direction, resulting in birefringence, meaning that the deformed area will exhibit two different refractive indices. This will result in a relative phase retardation between the two waves, and that explains the color change we observe in this lab. We plotted the graphs of the horizontal stress and vertical stress versus the distance from the center of the hole based on the experimental data. But we only had 5 points to plot each graph. Also, the SOLIDWORKS finite element analysis was conducted under ideal conditions. So the graphs don't look so perfect, but they're pretty much consistent.